Thank you, Boumediene, for the introduction and the invitation. So, okay, so the talk is going to be basically split in two parts. So, in the first part, I will talk. You will see the progression. I mean, that's I don't like to do sort of spoiler alert. I'll go with the flow, and please interrupt me if you have any questions, or if you prefer to ask at the end, as you prefer. Okay, so I'll start with some basic facts. So first fact is that differential equations are basically everywhere, and they're a dominant modeling mechanism throughout science. On the other hand, neural networks and deep learning have revolutionized technology in recent years, over the last decade. And it turns out that there are deep connections between these two areas, between differential equations and neural networks. And rough paths, or rough analysis more generally, which was initiated by Terry Lyons in the late 90s, represents a robust solution theory for differential equations. And I will try to explain what kind of role it plays in this connection between neural networks and differential equation. Okay, so I'll start with ordinary differential equations. So the first remark that got this whole field is a recent field. Okay, it's in 2018. It was one of the initial papers that highlighted this fact that many neural networks can actually be interpreted as approximations or discretizations to differential equations. And the architectures that was considered in this first paper was the one of a residual neural net that is defined recursively in this way. So yn is the output of the nth layer of your architecture, and this yn plus 1 is the output of the n plus first layer, and the two are related via this equation, where f theta is a parametric function. It's called the residual block, that is usually a generic neural network that can change every iteration and acts on the output of the nth layer. And it's fairly straightforward to see that if you consider the ordinary differential equation dy f theta t y t dt, and you apply a simple Euler scheme to it, well, then you retrieve basically the discretization that defines a residual neural network. Now, the neural networks are usually paired up. I mean, they're usually deployed in supervised learning to forecast or to forecast things, and but being dependent on a certain number of parameters, well, they need to be trained, right? And the way that these models are trained is via a loss function, so a criterion that tells you how bad or good job you're doing in your prediction, and by gradient descent, this loss function is the parameters of the neural net are optimized by gradient descent, and usually, and in the context of neural ODEs, which are this sort of continuous time analog of ResNets, the pipeline, the typical pipeline, would be to evaluate the loss function at the output of your neural AD. So the output yt1 of your neural AD is simply the solution at time t1 of an ODE with a vector field modeled by the neural network f theta, and with initial condition yt0. And this ODE, neural because the vector field is f theta, this ODE can be evaluated by calling. So this should be an approximation, because it's just an approximation, by calling any ODE solver of choice. And in particular, the ODE solver can be treated as a black box that takes as an input the initial condition, the vector fields, the initial point in time, and the final point in time. And then when it's called, it produces the solution at time t1 that then gets fed into the loss function. Okay. Then the optimization, so the gradient descent, requires, as the name suggests, the computations of the critical quantity that is needed for backpropagation is the derivative of the loss with respect to the parameters of your neural architectures. And in this talk, I will denote by AT theta this quantity. Sorry, this should be AT1. Now, in order to obtain this quantity, well, in this Neural ODE paper, the authors introduced an auxiliary quantity, which is called the adjoint process, that will be useful, and I will explain how it's going to be useful in the next slide to obtain the quantity of interest, which is this gradients, A theta t. Now, this adjoint process is defined as the derivative of the loss function evaluated at the final point of the ODE, but not with respect to the parameters of the neural net, but with respect to the intermediate values yt of this of the ODE, of this dynamical system. And relatively recent but quite classical results from Triagon in 62 says that if you consider, well, this Triagon didn't consider this result in the context, of course, of neural networks. So this is in some sense is a result that is was adapted by the authors of this Neural ODE paper in the context of learning. So if you consider a neural ODE of this form, where the vector fields satisfy appropriate Lipschitz conditions, then you can show that the adjoint process, once again, this quantity here, satisfied also an ODE. It is actually a linear ODE. So this is quite a useful fact, because what you can do is that you can compute, you can compute the value of this adjoint process at time t0 by another call to an ODE solver, but this time run backwards. Okay, you start from t1 and you start from the initial condition at time t1, which is at1, and then you run the ODE solver backwards, because the at solves an ODE, to obtain the value of this adjoint process at time t0 by simply solving this ODE, which is, this is just equivalently the same thing as above, but written in integral form. Okay, so now what is the link with the actual quantity of interest that we need for doing backpropagation, which is this A theta t? Well, you can show that in a very similar way to how the adjoint process ODE was obtained, you can show that this AT theta process solve this equation. So it's the derivative of this process is equal to minus the adjoint process that was obtained above times the derivative of your neural net with respect to the parameters. And this means that the crucial quantity of interest for backpropagation, which is the derivative of the loss with respect to the parameters at time 0, is simply equal to minus the integral from t1 to t0 of at times the derivative of theta with respect to theta dt. So, long story short, if you, one of the nice properties of a neural ODE that is that in order to be evaluated, a neural ODE consists in simply evaluating an ODE, so solving an ODE by an ODE solver. But then, in order the backpropagation mechanism, so the obtention of this quantity of interest here, also can be obtained by solving another ODE. So in other words, the forward and backward pass of this neural architecture can be obtained by simply solving an augmented system of ODEs. Now, this is one way, which is called the adjoint, and now it's, people call it this adjoint sensitivity method to compute gradients and to run backpropagation through this neural ODE model. It's not the only way, because of course, if you go back to the definition of a neural ODE, when you implement your ODE solver of choice, which can be Euler, it can be Ranch-Kutta, can be fancy implicit solvers or whatnot. At the end of the day, the numerical solver will be constructed by linear algebra operations. And provided that these linear algebra operations are implemented in a backpropagatable software like TensorFlow PyTorch, it's very possible to backpropagate directly through the operation of the ODE solver. And depending on what, in the situation and data situation that you have at hand, one choice of backpropagation, either the direct one or the adjoint, the one based on adjoint, can be one can be more suitable than the other. But at least there is this nice, in some sense, elegant alternative way for doing backpropagation through this this kind of model. Now, the next element of this family of neural differential equation models that I plan to discuss in this talk is goes a little bit more towards the spirit of rough paths, and let me explain why. So instead of considering a ResNet, let's consider a recurrent neural network, or rather a residual version of a recurrent neural network, which is given by this equation. So this is very similar to a ResNet, but with the difference that the residual block is a function not only of the iteration and of the output of the previous layer, but also of an external stream of information that might influence your system. And RNNs are, classically used to process sequences of data. Okay, so these are, you all know the utility of RNNs. Now, it can be shown, I mean, it's not immediate to see why, but it can be shown that the continuous time version of an RNN can be formulated as a dynamical system, okay, that in our community we call the control differential equations, but it is a dynamical system driven by xt of this form, and where xt is where x is a function from 0t into Rd, which we refer to as a path, and in particular is a continuous path that drives the dynamics. Of course, when this path is obtained, usually obtained from data, so data is discrete, it's a sequence, discrete sequence. This path is obtained, for example, by your favorite interpolation techniques, piecewise linear, piecewise constant, cubic splines, or whatever. And the mechanism of a neural control differential equations, which is this dynamical system where the vector fields are again parameterized by a neural net, is summarized by this picture. So you initially have your discrete sequence of data that is interpolated into a continuous path. This continuous path drives a control differential equation with dynamics given, with vector fields specified by a neural net, and the solution of this control differential equation is the output of your model. And then depending on the applications that you have at hand, you might be interested in looking at the solution at final time, or you might be interested in looking at the solution pathwise, so the whole response path, depending on what kind of applications you're interested in. Now, the question is it possible to obtain, in a sense, an elegant way of backpropagating through this neural control differential equation model in a similar way as we backpropagate through a neural ordinary differential equation model? And the answer is yes, and it's given by this statement. So here I've formulated a neural CDE where the vector fields are defined element-wise. So because xt is a multivariate path, so this notation is equivalent to the previous one, but it's just written coordinate-wise. It's just more explicit. So if you consider a neural control differential equation of this form, where xt is a continuous path of bounded variation, and where each vector field is bounded, and well, it satisfies some regularity conditions. So in particular, bounded, differentiable, and with bounded first derivatives, but this can be relaxed, this condition. And you consider again a differentiable loss function, okay, that acts on the output of this neural control differential equation. Then it can be shown that the adjoint process, which is defined exactly in the same way as for the ODE case, so derivative of the loss evaluated at the solution at final time with respect to the intermediate values of your dynamical systems, it can be shown that this quantity, which is crucial for backpropagation, once again, satisfies also a linear control differential equation. So backpropagation through this can be carried out, once again, in an efficient way by solving an augmented system, now this time not of ODEs, but of CDEs. Okay, right. Now, among the, among control differential equations, there is a family of differential equations that is of particular interest, especially in stochastic analysis. And this is given by, of course, stochastic differential equations. So stochastic differential equations are control differential equations where the control path is a Brownian motion. So, but this needs a bit more structure. So, so a neural stochastic differential equation, and here I'm considering SDEs interpreted in the Stratonovich sense, and I will explain. Sorry, let me close the door because, yeah, that's better. Sorry. So I will consider a stochastic differential equation in the Stratonovich sense, and I will explain in the next few slides why precisely the Stratonovich sense. So it's a model of the form. I mean, this, you see it coming, is of this form. Okay, so it's an SDE with drift mu theta and with diffusion sigma theta, parameterized once again by neural networks. Like this. Okay, so mu theta is a neural net that acts on time and yt and returns something of the shape of yt, and sigma theta is a neural network that acts on time and yt once again and returns a linear map, a matrix that acts on the Brownian motion and returns something of the size of yt. And W is an m-dimensional Brownian motion. So you can show this is classical results. I mean that if the drift and diffusion are Lipschitz, and then you have finite variance, then there exist unique solutions to this SDE. And from a machine learning perspective, before getting into more mathematical considerations, from the machine learning perspective, these neural SDEs are interesting because they can serve as more or less canonical generative models for time series. And this is how. So a generative model is simply a model that consumes a sort of manageable distribution, usually a Gaussian distribution. It morphs this distribution via a push forward function that is usually parameterized by a neural net into a generated distribution. And then the generated distribution is matched against an observed true distribution by means of a discriminator. And then the whole thing is trained adversarially or non-adversarially, depending on which, if you're using a GAN or a variation autoencoder and so on and so forth. But the moral of the story is that when you are interested in generative modeling for time series data, so suppose that you have a bunch of stock prices, and you're interested in sampling additional sample paths from this empirical distribution of sample prices. Well, one way of doing it is by using a neural SDE as a generator. So you start with a Brownian motion. You solve an SDE driven by this Brownian motion, parameterized in this way. You obtain sample paths given by solutions of this SDE, Y. And then you try to match these sample paths against the true distribution, well, true in the sense of observed data distribution that you have available, by means of your favorite discrepancy, be it KL, Wasserstein, MMD. Here, I don't have time to describe all the different options that can be used as a discrepancy, but you can see that these neural SDEs are can be used to achieve this goal of generative modeling for time series. Now, a more or less natural question that might arise given this, given the progression that, of this talk is it possible to obtain an adjoint method, so to backpropagate through the operation through a neural SDE in a similar way as we backpropagated through a neural CDE? And the answer is, well, is not that straightforward, because if I go back to the previous theorem, a crucial assumption for this theorem to hold was that the driving path xt is continuous end of bounded variation. In particular, as some very strong, in a sense, regularity condition. And this, if these regularity conditions are violated, so if the path, so we have a way of understanding the roughness of the path. So there is a quantity that is called p variation, or other people, I mean, there are different ways of measuring the roughness of a path. P variation is one way, alpha order regularity is another way. No matter which metric do you, or which quantity do you use in order to define the regularity of a path, you have to face a threshold. So if the path, in terms of p variation, if the path is of finite p variation for p less than 2, then there is classical theory allows to make sense of objects of the form integral of f of yt dxt, provided the f is smooth enough. There is no problem in defining an integral of this form using either Riemann-Stieltjes integration or Young integration. Now, whenever the x starts to be rougher than this threshold, so in particular in terms of p variation, it's of infinite p variation for any p less than 2 and finite p variation for some p greater than 2, then Riemann-Stieltjes and Young integration are not enough anymore to make sense of this object. So, and this is precisely where rough path theory comes into play. And so here, these are basically textbooks that not introductory. These are the Fritz and Heyer and these lecture notes. Some few are more high level, precise but still high level textbooks for this theory. And Fritz and Victoire is it's a much more complete, in a sense of depth, mathematical depth textbooks for if you want to go more into the details. Okay, so let's see. So I'm not able to, of course, would be too pretentious to encapsulate the whole of rough path theory in an hour talk, but for the context of neural differential equations, and in particular neural stochastic differential equations, this is the sort of result that I'd like to present coming from rough path theory. So before going through the details, I'll try to explain it at a high level, and then we can look at the details. So basically, this result is telling you that if you have a Stratonovich stochastic differential equation, what you can do is that you can consider, so driven by a Brownian motion, what you can do is that you can consider a smooth or piecewise linear approximation of the Brownian motion that agrees with the Brownian motion on a given uniform grid. Well, it doesn't need to be uniform, on a given time grid almost surely. So you get this smooth approximation of Brownian motion. Then you can look at the sequence of approximations when the size, when the time steps of the grid goes to 0. What you can show is that the sequence of piecewise linear approximation of Brownian motion converges to a limiting object, converges in a specific topology, this p-variation topology, to a limiting object that is a rough path. And this in particular is called an enhanced Stratonovich Brownian motion rough path. Well, that's one thing. Now, the other, by doing that, what you can do is that you can go back to this sequence of approximation of Brownian motion. And what you can do is that you can consider the differential equations driven by this sequence of approximations. So if you consider differential equations driven by this sequence of approximations, these are simply ODEs with random coefficients, because you're able to differentiate the approximation of Brownian motion. And so these dynamics are completely understood in terms of ODEs with random coefficients. And now the beauty is that what you can do is that you can solve with classical theory, ODE or CDE theory, this sequence of ODEs. And then what you can show is that the solution of, the solution of each of the element of this sequence, so the sequence of solutions in a sense, converge in p-variation to a rough path, okay? But more importantly, it converges in probability to a stochastic process that turns out to agree with the strong solution of the Stratonovich SD. So in other words, you have this nice approximation of your limiting object that you're interested in, which is this SDE with Stratonovich SDE, in terms of a sequence of random ODEs. This is one of the, this is called the Wong-Zakai approximation. Let's go through this in more details. So you have your drift and your diffusion that needs to be smooth enough. So it needs to be, so Lip1 means continuous, Lipschitz continuous. Lip2 is stronger than Lipschitz continuous. I'm not gonna give into the details of what is meant to be a Lip gamma function, but you can think of it as Lip2 sufficient condition is that the function is bounded and the first derivative is continuous and is also bounded. Now now consider, as I said, the sequence of approximation. So for example, piecewise linear paths that agree with the Brownian motion on a grid of endpoints almost surely, okay? And let Yn be the solution of the random ODE driven by this approximation of Brownian motion. And once again, there is no problem at all in understanding this object with classical theory. Now, what rough paths tells us is that the sequence of solutions of these random ODEs converge to a limiting process, okay, Y, which turns out to coincide almost surely with the strong solution of the Stratonovich SD, which is the thing that we are interested in the first place. And well, furthermore, there's much more. So furthermore, the solution, so the Ito map is continuous in the p-variation topology, and furthermore, this result is actually generalizable to controls that can be much arbitrary rough, so much rougher than Brownian motion. So you have a similar universal limit theorem or Wong-Zakai approximation for not just for SDEs driven by Brownian motion, but for rough differential equations driven, for example, by a fractional Brownian motion with the Hurst exponent arbitrary small. Sorry. Okay, so now that we can approximate, use Wong-Zakai to approximate a Stratonovich SDE using a sequence of random ODEs, well, then it's quite promising, and we can, we know how to, use. We know how to. We know that for a random ODE, we know that the adjoint process satisfies also a linear control differential equation. This was the theorem above. And now, thanks to this, obviously here I haven't put the proof, but this is the crucial fact that one can leverage in order to obtain, an adjoint equation that which is the object of this theorem for stochastic differential equations. So more precise for neural stochastic differential equations. So more precisely, let once again this time mu theta be a neural vector, a neural drift, so a drift parameterized by a neural net with the appropriate conditions, and sigma theta as well, a diffusion coefficient parameterized by a neural net, and we consider the Stratonovich neural SDE of this form. Now, once again, we let L be a differentiable loss function, then it can be shown, surprise, surprise, that the adjoint process coincides almost surely with the strong solution of the linear Stratonovich SDE. So basically, the adjoint process nicely extends not only to SDEs, but actually can be generalized to rough differential equation driven by arbitrary rough controls. Okay, so there are many details that I have not both from the rough path perspective and from the machine learning perspective that I haven't discussed. Some of them are how to choose the vector fields, so the drift and diffusion in a neural SDE, how to impose Lipschitz conditions on these things. This is something that I haven't discussed. What choice of a numerical solver one can use, right? Both for the forward pass and backward pass, right? And well, this can, in order to do this, we can inherit from a long history of development in numerical analysis over the last 100 years or more. So you have your Euler, Ranch-Kutta, and all the fancy solvers for differential equations. And of course, by now there is an abundance of different software available for training these neural differential equation models in different languages, PyTorch, now JAX, Julia, and not. Okay, so this is basically the sort of end of the first part of my talk. I don't know if there are any questions at this point. They're not. What I wanted to.
Well, maybe.
Yes, hi.
Very nice development of many concepts and so on. But how is this consisted or envisioned by Pontryagin theorem? About the Lipschitz, you had a footnote about the Lipschitz, but it wasn't direct to what I was thinking about. How do you keep along the development the Lipschitzness?
What do you mean? Sorry.
Well, when you do the compromise of piecewise linear, this, to me, it means that you're trying to at least tangentially be consistent with the requirement in Pontryagin theorem.
So if I understand correctly, you're asking how does this theorem here can be applied in order to obtain this theorem here. Is that your question?
Well, I didn't absorb the theorem so quickly.
Yeah.
To be modest here, and you, of course, are delved in it. But what I'm asking in a very general way, there is a fundamental theorem by Pontryagin that you referenced, right?
Yes.
Now, this development has to be connected to this theorem all the way, because we don't argue with Pontryagin.
No. I'm not sure I understand what you mean by development.
All this talk that you made,
Okay.
okay, there is something called, it has to be Lipschitz. It has to be continuous. So the rough pass and all this amazing work by Terry Lyon and yours has to be compatible with that.
For sure, yes. So the Lipschitzianity conditions are imposed on the vector fields of these differential equations. So in a sense, you know, one remark, I guess, is that one has to be ready to accept that the rougher, you know, the more irregular the control is, the smoother the vector fields one has to pick in order for the dynamics to be well defined. Because, and this is actually something that you know, it's visible or in the assumptions of this theorem. So you see that, for example, the drift is less regular than the diffusion, okay, because the drift is lip 1, which, you know, is less regular than lip 2. So one has to one has to use a higher level of smoothness on a vector fields that hits something which is, in this case, is Brownian motion, which is much more irregular than simply your linear control that is given by time. So the smoothness assumptions or the Lipschitzianity assumptions on the vector fields of your dynamics have to be compatible with the roughness of the control that you're using. So that's one remark that maybe goes in the direction that you were mentioning. Then
that helps a lot. Thank you.
Cool. Yeah, no problem. So now I wanted to, let's see if I can do, yes. So
I have a question.
Yes, hi, sorry, yes.
I had a small question. So does the lip2 condition include differentiability in it? I think it does, right?
Yes.
So,
yes.
So if the lip2 condition includes differentiability, doesn't that immediately rule out neural networks can't be a part of that theorem?
No, because if you use tan H, everything is differentiable. No, I mean it's.
But then that's a very unrealistic regime of the theorem.
No, but I mean, there are standard ways of imposing. Well, not standard, but there are ways of imposing these Lipschitzianity constraints. They're not easy to impose, but there are ways to. For example, you can take if you take a Lipschitz. If you take weight clipping and if you take Lipschitz nonlinear activation functions, you can show that the corresponding neural network is a Lipschitz functions.
The Lipschitzness is true for every activation in U. So Lipschitzness is not the bottleneck. The bottleneck seems to be that there's a differentiability condition in your loss function and in your lip2 condition. You're assuming the loss is also differentiable, right?
Yes, 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 absolutely.
So that's differentiability in the weights of the neural network, if I'm not wrong. You're assuming the loss is differentiable function of the weights of the net.
No. The loss is differentiable with respect to its input.
The input is what here? The input of the neural net or input as weight of the net?
So the input of the loss is.
Isn't it differentiability with the weights of the net? You're assuming?
No. The differentiability with respect to the weights is something that is well, okay, but okay. If you want, then you need to use the chain rule, right? So I mean, at the end of the day, what you want is that you want the derivative of the loss function evaluated at the output of your neural net, acting on the input of your neural net with respect to the weights, okay? And then you can, by using the chain rule, I mean, this is just basic backpropagation stuff.
No, so isn't the differentiability assumption of the loss function assuming that the gradient of the loss with respect to the weights exists?
So okay, so the loss is a function that acts on a vector.
Yes, that vector is a function of the neural weights.
But that vector is not the weights. That vector is the output of your net.
Yes.
The loss function acts on the output of your net.
Yes. So, but the differentiability assumption is on the weights, right?
No, the differentiability assumption is on everything. The loss needs to be differentiable because
with
then
respect to which variable?
So
this will be the input or the weight of the net.
L of f theta of y. Okay,
yeah,
and
so
then what you want, so this of x, say, no? So this is equal to L of x of y. Okay, so where y is f theta of x.
Yes.
So what you want is that you want the derivative of the loss with respect to the weights, right?
Yes.
And this is equal to, well, you use the chain rule, right? dl d theta, this is dl dy, dy d theta.
Yeah.
Right?
So this is if this equation is being assumed, that means you cannot use a ReLU activation immediately. That means the most basic activation is not a part of the theorem because these equation cannot be used for ReLU.
Yeah, okay, but yes. But
yes,
then...
So that means my problem is that the theorem doesn't seem to be at all neurally sensitive at all. Like there's nothing neural about the theorem, it confused them.
What do you mean? There is not, which theorem and what do you mean by neural?
I mean, what I'm missing is how does the theorem change if I change the neural network? Like, where is that sensitivity?
I mean, I don't understand the question. I mean, when you have a neural network architecture, you fix your architecture, you fix your activations, you fix your loss function, you give me data, and then you do backpropagation.
Yes.
Right? So what's the question? I don't understand.
I'm saying if I replace mu theta and sigma theta by a non-neural function which satisfies lip1 and lip2 condition,
okay,
the theorem would still hold.
Yeah, absolutely.
And so that's a problem, right? Because now the theorem is not neurally sensitive theorem because there is no parameter dependence in this.
I see what you mean.
There is no dependence of the neural architecture or the weight structure in the theorem's conclusion.
Yeah, absolutely. I see what you mean. So the answer to that is basically the thing that I said here. So this adjoint process, which is the once again is the derivative of the loss with respect to the intermediate values of your model, not with respect to the weights. So here there is no weights. So this can be this process can be defined even if the vector fields are not neural nets. This is a process that is called the adjoint and is independent on the fact that you're parameterizing with neural nets or not, right? So it turns out that this process is the crucial process that you need in order to understand the quantity that you are interested in when you want to do backpropagation. And the link between a theta t and at is this one. So once you have at, and once you know how, obviously you know how to differentiate the neural net with respect to the weights, because this is just simple chain rule, then you can just integrate the at, you can just compute this, the quantity that you care about from the quantity that I'm discussing throughout these slides, so this adjoint process, using just integrating. So that's why I'm focusing on this on the adjoint process, which is, I understand what you're saying, is not the dependency on the weight is absent, of course, for this adjoint process. But then the quantity that you need for the backpropagation is a simple integral of that adjoint process. So it's very easy to obtain the quantity you're interested in if you know what's the adjoint process. Does that answers your question?
Not really, but okay, let's continue.
Okay. Right. So now what I'm interested in from the second part of the talk is something more complicated. So this picture corresponds to a dynamical system. So the left-hand side is an initial condition. So this is let's say an initial configuration of a fluid. The picture in the video in the middle is a random forcing that influence the systems. So for example, can represent uncertainty, or can represent, for example, local random fluctuations that influence your fluid, or any other system that you want to study of this form. And then on the right-hand side is the actual the solution of your dynamical system. So for example, the behavior of a fluid. So what's the difference between this sort of dynamics and the ODE, CDE, SDE dynamics that I've discussed so far? Well, the dynamics that I've discussed so far, the solution U at time t takes its value in a finite dimensional space. Okay, so the UT is a vector in Rn. In this case, if I stop the video like this, the solution is a function of space. And the motivation for the recent work about neural SPDEs is can we extend the mechanism for finite dimensional state spaces that ODE, CDE, and SDEs can handle to situations where the dynamics are not valued in a finite dimensional space, but they're valued in an infinite dimensional functional space, like in this case, like in the case of SPDEs. This is just a simple motivation. I'm going to get into more details, hopefully now. So let's get into this setting. So D now it's a bounded domain. So it's a D-dimensional subset. It's a subset of RD and is bounded. And now HU will represent the state space of my dynamic. So now HU is not a finite dimensional vector space, but it is a Hilbert space of functions. So the dynamics that I'm going to consider in a second at time t will be a function of this form, will be a function of space with values in RDU. And similarly, the state space of the control is also going to be a Hilbert space, an infinite dimensional Hilbert space of functions. And then we are in the, we want to locate ourselves in the realm of stochastic partial differential equations, which can be written in more or less general form, or rather these are stochastic PDEs of evolution type, okay? Where, this WT now is not a finite dimensional Brownian motion, but is an infinite dimensional Wiener process. Okay, there is a lot of theory behind this, but so the Q Wiener process, it means that you have a correlation structure in space. So actually, this process is smooth, is not smooth, but is somehow is regular in space, while cylindrical Wiener process is basically space-time white noise. So it's somehow is the most random object in space-time that you can think of. If you, I'm simplifying things extremely, but just to give the intuition of what is this this object here. So in other words, you can think of these WTs as Brownian motion, but with values in an infinite dimensional space of functions. Okay, and then the rest, the skeleton of the dynamics is pretty similar, not exactly the same, but pretty similar to the one of SDEs. So you have a drift F, and you have a diffusion G. Now these times these are not functions; they're not standard vector fields, so functions, but these are operators. Okay, so F is an operator that consumes a function of space and returns a function of space, whilst G is an operator that consumes a function of space and returns a linear functional from the Hilbert space Xi to the Hilbert space HU. So, this is the setting that in some sense generalizes the setting of SDEs. And furthermore, as if you sort of didn't consider this bit, then you would well, anyway, you also have of course your a differential operator, that spatial differential operator, usually linear differential operator, that generates an exponential semigroup, and C0 semigroup. So here, I'm not at all giving details because there would be too many of them, but here again, there are two introductory textbooks that, no, one is lecture notes that Martin Heyer 2009, and the other one is the same book as one of the previous three that I've mentioned. But so if that book is nice because the first part is about rough paths, and then the second part is about SPDEs and regularity structures. So that's the two references that one can look at. So, sorry. Okay, so there are as in with SDEs, there are different concepts and notion of solutions of SPDEs. And so the one that for various reasons is more manageable mathematically is the one of a mild solution of the SPDE. So so UT is called a mild solution of the SPDE above of this SPDE if U satisfies this integral equation. So U is e to the TL hitting the initial condition, which now is a function, plus an integral, well, the integral corresponding to the drift part of the equation, plus another integral corresponding to the diffusion part of the equation. And the crucial difference between this and the integral, in some sense, integral expression of an SDE is twofold. One, once again, I mean, I'm repeating myself, but F and G are operators and not functions. And then you also have the action of the semigroup that basically intuitively, the semigroup, what it does is that it's an operator that mixes information also in space. Because if you think of the integral expression of an SDE, the operation of integrating, the right-hand side of an integral expression of an SDE, what it does is that this is an operator that acts exclusively on time. I mean, time-wise. Whilst if you have also, if you want to understand spatiotemporal dynamics, where there is a dependency also in space, well, you need somehow to introduce an operator that mixes somehow information also in space. And this is at a very high level, intuitive level, that's what the role of this semigroup is. Okay, so the second integral here is not a Stratonovich integral, but is an Ito stochastic integral, okay, that can be defined in terms of Karunen Loewe expansion, but okay, this is the Ito stochastic integral. So actually for SPDEs, there is no notion of Stratonovich stochastic integral, because basically the correction that you would get from Ito to Stratonovich is actually infinite. So the Stratonovich stochastic integral in the case of an infinite dimensional noise doesn't make sense mathematically. So it's always Ito. And so here I'm, way less, precise in terms of assumptions on F and G, but it's classical more or less in the field, in the area of SPDEs, to have a well-postness result that ensure that there exists and unique mild solutions to classes of SPDEs, provided that, of course, F and G are satisfy regularity conditions, at least for short time intervals, short time horizons. Okay, now what I want to do is that I want to, of course, go towards application to data. So the first thing that I will do is that I will approximate the Wiener process W with with, in some sense, not necessarily a piecewise linear approximation in time and a smooth approximation in space. So this is basically the equivalent of a piecewise linear approximation to Brownian motion, but there is also an approximation in space. And this can be represented as this regularization can be represented by the action of a mollifier. Okay, so that's so basically it's like smooth. Think of it as smoothing this Wiener process. Smoothing in depending on the nature of the SPD, you need to take care of smoothing it enough in time and enough in space for things to behave in a coherent way. But let's not go too much into detail. So we consider a smooth approximation, okay, a mollified approximation of the Brownian motion. And instead of considering the original SPDE, what we consider is the random PDE, okay, that is driven by the smooth approximation of the Wiener process, okay? Which I can, of course, differentiate. Well, of course, I mean, that's the point of using a regularization, is that I can actually differentiate it with respect to time. And so I can rewrite the approximation of the SPD as a PDE with random coefficients, okay? Exactly the same way as with the Wong-Zakai approximation for SDs. Now, this enters very recent mathematical and very high. I mean, I'm not pretending that in this. So I'm way less familiar with this, with the theory behind regularity structures, and especially how to deal with singular SPDs and so on. But what I know is that, for example, you have relatively recent results that that tells you that if you do this. If you approximate your SPD with this random PD by using this smoothing or regularization of the white noise, then what you can show is that the random PDE u epsilon, okay, where epsilon is a parameter that controls by how much you're actually smoothing the Brownian motion, not the Brownian motion, the Wiener process. And when epsilon goes to 0, basically you don't smooth at all. Well, what you can show is that when epsilon goes to 0, the sequence of solution of the random PDEs converges in probability, of course, because you never get something easy, it converges in probability to a limiting process. But that limiting process is not at all what you expect it to be. It's not at all the Ito solution of your original SPD. It's actually the solution of an SPD, but with a modified drift. So the drift needs to be changed, which is to be expected, because that's what happens if you, also in the case of CDs, of SDs, if instead of considering Stratonovich, you consider Ito, then the Wong-Zakai approximation will converge to something that is not the Ito SD, but is with a modified, of course, it's the Stratonovich SD. So the drift, there is the drift correction from Ito to Stratonovich. So this correction of the drift is to be expected. But what complicates things is the appearance of these renormalization constants, okay, which are constant, so they're not too bad. But the problem is that they explode, they diverge to infinity as epsilon goes to 0. Okay, this is basically the leaving rough paths, which is already complicated, but at least it's nice because there is no pathological behavior and explosion and appearance of these nasty things, to the realm of SPDEs and regularity structures, where in order to make sense of the limiting objects of these approximations, well, you have to accept to introduce possibly infinite constants, renormalization constants, that to ensure well-posedness of your dynamics. I will make the link with with what will come in the final slides of the talk, but I'll come back to this at the end. So basically, the message here is that okay, a Wong-Zakai rough path approximation for SPDs, you can do it, but there are additional mathematical difficulties that arise from the presence of this infinite. Well, they're finite for a given epsilon, but they go to infinity when epsilon goes to 0, renormalization constants. But well, in my case, what I'm not going to consider the limiting the limiting nasty SPDE. What I'm going to consider is I fix a given regularization of the white noise, and I consider the corresponding random PDE. So that's the object, the dynamical system that I'm considering now. So, which is this one. Okay, I've just rewrote exactly the same thing as above, but I just eliminated the epsilon dependency just for easing notation. Okay, so now the goal of the next 5 slides, more or less, which I'll probably go quite fast because it's already 6, but Boumediene, you mentioned that could be go a bit above beyond 6, but
yeah, that's all right. Yeah. I mean, you have time, no worries. Yeah.
Okay. I'll try to
yeah. So people who have to leave, I mean, they can always watch the recording, so there is no pressure.
Okay.
Yeah.
Okay. So now the questions from a machine learning point of view becomes okay, how are we going to choose appropriate neural architectures to parameterize all the things that we need to parameterize in these dynamical systems, which are f, which is not a function, but is an operator, g, which is not a function, but is an operator too, and L. I mean, L, the differential operator L, and by consequence, the semigroup E to the TL. These are the 3 things for which we need to find appropriate neural architectures to parameterize them. So I'll start with F and G, because they're simpler. Well, they're simpler because I'm going to do I'm going to have some sort of relatively strong assumptions on them so that they're easy to parameterize. And then I will explain how to deal with the semigroup. So the drift and the diffusion. So in most of the SPDs that I know of, and I will show experiments at the end, these drift and the diffusions are nice in the sense that they're local. So what I mean by local is that, so an example, for example, I'll give you an example. So f of u equals f of ut equals ut cubed. Okay, this is a local, f is a local operator because if I want to evaluate f of ut at x, with f of ut is a function of space, so that I want to evaluate at a point in space x, then this would be ut cubed at x. But this is also equal, and this is what means to be local, this is also equal to ut at x cubed, right? So in other words, in order to evaluate the range of this f and g in order to evaluate the image of any function ut by these vector fields f and g at a point x, I don't need any additional information on any neighbors points of x in space in order to obtain the final answer. Okay, that's I mean, I guess the example is self-explanatory, and I'm not doing a very good job to explain it, but I'm sure, I mean, it should be clear. So okay, so assuming that f and g, so here I'm assuming that okay, I have the Hilbert space. So this, ignore this. This is I've already defined f and g, so this is redundant and it's not important. So so what it means is that okay, so for any h in so L2, so here I've assumed that the HU, which is this Hilbert space where the state space of the mild solution of my random PDE is, for simplicity, is L2. Okay, so squared measurable functions from D to RDU. For any function H, the action of F on H evaluated at X can be represented by a function, not an operator, a function f theta acting on the evaluation of H at X. Okay, that's what it means to be a local operator. And same thing for G. And so in other words, now I don't need to introduce parameterizations, operator parameterizations, but I can go back to comfortable, I mean, to my comfort zone and just use a parameterization for functions, because now the evaluation of H at X is just a vector. And so here f theta and g theta just need to act on vectors to produce, well, f theta another vector and g theta a matrix, okay? And so this can be parameterized by classical neural nets. So that's my way out for avoiding the problem of parameterizing these nonlinearities with, you know, with something that, you know, we know how to deal with. That's for f and g. Now the semigroup is it's more fun. So under relatively mild assumptions, it is classical that the action of this semigroup, et to the L, can be written as an integral against the kernel. So for any function h in the state space of the dynamics, the action of the semigroup on h evaluated at x can be written as the integral in space of a kernel. Well, the integral space of the function h against a kernel of this type. Okay, this is a fairly general family of semigroup that can be written in this way. Therefore, I mean, given this, if you want, you can take it as a definition of the semigroup. The SPDE mild solution, so that just let me this one, this is the definition. No, it's not the SPDE, it's the randomly forced PDE mild solution, can be rewritten in terms of the convolution, in terms of a convolution in space. Okay, so that's a convolution of the initial condition against the kernel at time t, plus the integral of this shifted t minus s kernel convolved with well, the right hand side of the mild solution of the random PD. Okay. Now what we can do is that we can use the convolution theorem. So that the convolution theorem tells you that the Fourier transform of the convolution of two functions is equal to the pointwise products of the two Fourier transforms. Okay, that's the convolution. And so by applying Fourier transform inverse composed with Fourier transform on left and right hand side of this equation, I get to this equation. So of course the left hand side remains unchanged, and the right hand side is this one. So f Fourier transform inverse times, okay, so here I'm going to apply the convolution theorem, which is here. So the convolution turns into the Fourier transform of the convolution is the pointwise product of the two Fourier transform. And okay, so here I can exchange integral and Fourier transforms. And here the Fourier again, the same trick. This is nothing fancy. Again, the convolution becomes the pointwise product of the two Fourier transforms. So here I'm just nothing. I haven't done anything special. But now what I can do is that I can consider, I mean, I've just I consider the argument of the Fourier transform inverse and call it VT. Okay, VT is just an element. It's just something in Fourier space. Okay, and now, and so this is the last bit of technical bit. So assuming that L, so L is this differential operator. So in an example is the Laplacian, okay? Or in another example is, I mean, usually L is a differential operator of polynomial form. If you consider differential operator of polynomial forms, you basically encompass most of the, certainly all the SPDEs that I know. So, you know, there's also a quite a generic assumption. So we consider L to be a polynomial, a differential operator of polynomial nature. So you can show that if L is a polynomial, then the Fourier transform of the kernel, which is the crucial, well, crucial is one component that we actually need to understand for in this expression. Well, you can show that, first of all, the Fourier transform of this kernel is an exponential of T times a complex matrix A. And thanks to this observation, what you can show is that VT, so the argument of this expression of the Fourier transform inverse on this expression here, solves an ODE, solves an ODE in Fourier space. So you can show that the dv dt is equal to a VT plus this expression, the Fourier transform of f theta applied to the Fourier transform inverse of dt plus g theta applied to the Fourier transform inverse of dt times psi prime. Okay, so this is, you know, shows some dynamics solved by the argument of the previous expression obtained by applying this convolution theorem. Now, of course, in practice, when I take Fourier transforms, I'm mapping a square measure. So first of all, L2 that's why I've assumed that the Hilbert space of functions is L2, because L2 is stable under Fourier transform. So if you take Fourier transform of L2, you get L2, and then you can take Fourier transform inverse of L2 and you get back to L2. So that's nice because you then never leave L2. And so in practice, when of course the Fourier transform is implemented by the fast Fourier transform, but that's just a detail. But in practice, what you get is that your Fourier transform is a function on frequencies, and you select a maximum number of frequencies. And so, in other words, the Fourier transform of a function can be represented as a finite dimensional object specified at a maximum that is maximum in the sense that is chosen by the user number of frequencies. Okay, and so what I can do is that if you can do that, then you have this ODE in Fourier space, okay, that I can solve, I can evaluate exactly the same, provided that I truncate the frequencies to a maximum number. I can evaluate using an ODE solver in exactly the same way as other, as previous ODEs. So an ODE solvers with this initial condition, with these vector fields, okay, with the vector fields is obviously given by the right-hand side of the ODE, and over the interval 0t. And so what I can do is that I can evaluate, okay, I can evaluate my model, my random forced stochastically, my stochastically forced PDE model by simply applying the Fourier transform inverse onto the output of an ODE solver with this specific configuration. And so this, what this tells is that, okay, so we not only we have a way of evaluating this neural SPDE model using ODE solvers, but of course, given that and Fourier transform inverse and fast Fourier transform in practice, but backpropagation can also be carried out using the adjoint sensitivity method that I presented in the previous slides. So this inherits all the computational advantages that were obtained in the previous finite dimensional differential equation models. Now, there is also this Fourier transform and Fourier transform inverse, but this, of course, are implemented, as I said, they're computed in practice with the fast Fourier transform, which is again linear algebra, and so it's trivial to backpropagate through the operation of a fast Fourier transform. And you have implementation everywhere in PyTorch and TensorFlow, very efficient. Okay, so that's, again, there are many details that I haven't discussed. So one of them is that there is another way. So first of all, that this is nothing fancy. I mean, this is actually something classical for solving SPDEs, which is called Spectral Galerkin schemes. So basically you take Fourier transform and then you solve an ODE in Fourier space and then you pull it back with the Fourier transform inverse. This is something that is a classical scheme, not only for SPDEs, but also for PDEs. And it's just that it turns out that this version that we built is actually a neural, if you want, I mean, in quote, a neural version, because, you know, all some of the components of it are parameterized by neural networks. In the paper, we also looked at a different way of evaluating the model. So instead of having an ODE in Fourier space, we can show that you can evaluate the model also by solving a fixed point problem. And for fixed point problems, you have very similar adjoint, well, it's not adjoint, but elegant way of backpropagating through the operation of a fixed point solver, which are very similar to the ones of a differential equation solver, but I can't go more into the details. Properties of the model is something interesting for, you know, computational PDE people, is space-time resolution invariant. So here, for example, we have trained the model. So which one is it? So yes, so we have trained the model on using data discretized on a 30. So this is two space dimensions, okay? And we've used data discretized on a 32 by 32 grid. But then once the model is trained, it can be, thanks to the, well, I cannot, these are extra data that are not discussed, but the property, the model enjoys the property that it's called zero-shot super resolution. So once it's trained on a given discretization, it can actually be evaluated on a different discretization, which can be finer, of course. So obviously, if it's finer, it's more interesting because of course the problem for computational PDE, one of the problems is that if you use too much, you know, if the discretization grid is too fine, then the computational burden is too high. If the computational grid is too coarse, then computations are not accurate enough, and so you can get blows up or different kind of numerical instabilities. And so this is, you know, one nice, you know, sort of compromise that can be achieved with the model, with our model. Okay, and then very quickly, I'll show you some experiments. So, so we considered we applied this Neural SPDE model on 3 supervised learning settings. So the first setting is, so these are all simulated data. Okay, so the first learning setting that we considered is the one of learning the operator mapping the initial condition, which is a function, to the solution of the SPDE, assuming that the driving noise is not observed. So there is an underlying noise that you know, that influences the dynamics, but in the learning procedure we don't take it into account. So of course this is a very, very hard task, and as I will show, all the models, all the benchmarks that we consider, including ours, failed. I mean, but this is the point of you including this setting, is that the noise is important. So we wanted to emphasize the importance of the influence of the noise, that is not there just to, you know, as a decorative element, but is actually, if you don't take it into account, you cannot learn the dynamics. The second supervised learning setting we consider is the one of learning the operator mapping the noise to the solution. U, assuming that the initial condition U0 is fixed across all the samples that we consider. So the physical system always starts with the same configuration. Okay. And then the third, which is the more, in some sense, the final one, is the one of learning the operator mapping the noise and the initial condition, both the pair, to the solution U. Okay, and then now I have three. I'm going to go fast on this. I have three examples of SPDEs that we simulated data from, and then we hid them. So the standard way of this sort of physics-informed deep learning methodologies that you have dynamics, and then you simulate trajectories from these dynamics. Then you hide the PDE, you forget about it, and you try to, from the sample trajectories that you've generated, retrieve or learn the PDE or the SPDE in this case. Okay, so this was the first. So here is the standard advertising performance that you need to publish in these machine learning conferences. So of course we do a better job than everything else, but I don't want to spend too much time on it. But it's quite big, the gap between us and everything else. So it's good, but you can there is no point in hammering too much on this. But one of them is this, maybe the stochastic Navier-Stokes equation in 2D, which is, I thought when I started the project, this would be a very difficult equation. And then after we were successful on this, I discovered that real hardcore fluid dynamics people like Dan Krizan and others in Imperial, for example, that we're talking with, they have equations compared to this, when this one compared to that is a joke. But anyway, okay, so one cool point about the model is that the evaluation of the model, so in order to evaluate the model, the evaluation of the model is actually extremely fast. So there is two, sometimes three orders of magnitude faster than classical SPD solvers that we had to use to simulate the data. And so then it depends on which evaluation method, and it also depends on, of course, on the discretization and the time step of the differential equation solver, and on many different parameters. But for the setting that worked well the setting that where the experiments were realized from, these were the speed up numbers that we obtained, which is quite nice because it's possibly something that could be interesting for computational PDE people. And then this is the last slide. I just wanted to finish with a lot actually of open questions that we have. And some of them are theoretical, some of them are practical. So, in the case of finite dimensional rough differential equations, we have this Wong-Zakai approximation. So you can find this sequence of random ODEs that converge to this limiting rough differential equations. And you can show, well, you have that. Now, you can actually show that if you have a stochastic PDE where the noise is finite dimensional, you can have exactly the same. I've already said that the E Stratonovich makes sense in the case of finite dimensional noise, even for SPDEs. And you have an analogous Wong-Zakai approximation also for those. Now, when you go to infinite dimensional noise, then it's much more complicated, as you saw with the example of the stochastic heat equation. So the first question is, if we used a random PDE model. So one question is, does the random PDE model, when the size of the support of the modifier goes to 0, with the smoothness of, you don't smooth at all, the Wiener process, does it converge to a limiting process? And that process the solution of an Ito SPD? And which SPD? This is all, we have the results that I showed you is for a specific PDE, SPDE, but what happens for our our neural SPDE? That's an open question. Is the solution map, so the map that maps the noise onto the solution of the SPDE, continuous with respect to some topology? I mean, this is something that you really want in machine learning. You want to ensure, because for different reasons, for stability reason and so on, that the class of approximators that you use is continuous in some sense. Is it continuous in the limiting object, not the random PDEs, but the limiting object we don't know? Is it continuous? Is it the limiting process? Is it independent on the choice of modifiers? Different ways of smoothing the white noise, right? And in the classical rough path Wong-Zakai, you know, I've mentioned this piecewise linear approximation of Brownian motion as an approximation, but actually you can show that no matter how you approximate the Brownian motion with smooth bounded variation path approximations, at the end, when the size of the partition goes to zero, of the time grid goes to zero, you get the same limiting object. So it is independent on the modifier, on the regularization. Is it true for the case of SPD, for the case of our neural SPDEs? Well, this maybe I can skip this because it's a bit more technical, but about renormalization, because you know these renormalization constants are, you know, it's very, you know, they're hard to obtain from mathematically. So is it possible to use this neural SPDE architecture to actually learn this renormalization constant? We somehow are natural, appear naturally in physical dynamics, but that are very hard to sort of get hold of from a mathematical perspective. And it's possible to learn them somehow. Now, I mentioned that neural SDEs were used primarily as generative models for time series, right? So neural SPDEs could be, I mean, at least, you know, we haven't done it, but would be good that if they could be, you know, they could serve as generative model, not for time series, but for spatiotemporal signals. Now, the problem is that there is no, I mean, as far as I know, there is no discrepancy or, you know, discriminator. Like, you know, for the neural SDEs, we had Wasserstein, KL, MMD, and so on. What about spatiotemporal signals? Is there any natural discrepancy between distributions supported not on paths, but on spatiotemporal signals? So this would need to extend all these discrepancies to spatiotemporal data. And finally, can these neural SPDEs be used for not processing linear processes or for solving SPDEs, but can they be used to process videos or images, right? And so data that has nothing to do with physics or differential equations, but you know, things like videos and images. And I'm sure there are other questions, but yeah, that's the end of the talk. If you have any question.
All right, thank you very much. Thank you. Any questions?
You can see on the chat.
I have one question.
Hello, yes.
The differential equations on which you were testing them, if we switch off the noise, it's a homogeneous differential equation, right? All the examples. I mean, there is no forcing function in any of them, if I understand correctly. Or there is a forcing function F.
All force, yeah.
So there is a F, okay. So when you're comparing against DeepONet, are you comparing like for different forcing functions? Is that how the comparison is set up?
So you mean this F here?
Yeah. So because for the DeepONet, F is the real focus. DeepONet is focused about getting the F right. So I'm just wondering how the comparison to DeepONet is set up.
So if I remember correctly, we picked one F and we used the same F, generated.
Yeah. So you're basically comparing the DeepONet versus your method at a fixed F.
Yeah, but epsilon changes, right?
Yeah, but the deponent is tuned to get the, basically the whole point of the deponent is to say that if I change my F, my retraining time is 0. So what happens in other methods, one should ask them, if you change the F from F1 to F2, do you have to retrain your method from scratch?
No, because basically what you can do is that you can incorporate the F in the epsilon. And so instead of learning the operator from epsilon to U, you can learn the operator from the tuple epsilon F into U, or epsilon F and U0 into U, or whatever you want. You just...
No, but my point is, if you change the F, do you have to retrain?
Yeah. So if F is an input of the model,
yes,
you know, that you don't retrain.
That's why different F you have to retrain from scratch, right?
No. The model is so in this setting, yes, but because but if you wanted to have a fixed model that can accommodate different Fs without retraining, you just have F as an input to the model.
Yeah, then I think, yeah, I guess that so that's what is kind of a bit confusing when you when you compare to deponent, because if you say that, okay, then it's a different model you're comparing. If you say that, okay, let me now make F the input to your system, it's a bit unclear comparison.
No, but this because you have F, which is an additional forcing that can be incorporated in the much more complicated epsilon forcing. But okay, so but if you look at this, for example, of here there is the forcing is epsilon. Okay, so you can think of epsilon as the forcing.
So this Kotovic-de Vries comparison, there is no forcing function.
See, the forcing is epsilon.
No, but epsilon is not forcing, I would say. That's a noise. Noise is different.
No, epsilon is forcing. And that's the point. Epsilon is what forces the equation. But
Xi is a random variable.
No, but you can force. No, but we take realization of epsilon. So everything is pathwise. So if you have a forcing that is deterministic that you give to me, and then you want to learn not the operator from epsilon to U, but from the forcing to U, no problem. I mean, it's very analogous. It's the same thing. If you see what I mean. Epsilon is the forcing. That's the point. We want to accommodate for external, like CDEs extend ODEs, because there is an external inflow of information that influence the system, a forcing. SPDEs, do the same thing. You have this in this case, we choose a random forcing because that's the realm of SPDEs. But you can have deterministic forcing if you want. It's actually easier. But,
I guess one just think a bit carefully about how is the error then defined. Like, what is the 0.235 measuring then? I'm a bit confused. I'm very confused about the meaning of the 0.235 and 0. When you say Xi to U is 0.235, what is this 0.235 then? Is it averaged over different forcings?
Sorry, where 0.235?
I'm reading the second column of your slide, where it's Xi to U is 0.235. So what does that 0.235 mean?
I think it was the pathwise L2 loss.
So it's a pathwise L2 loss averaged over different forcing, or is it for a single forcing?
For a single, well, no, it doesn't mean anything for a single force, right? You have the input-output pairs of your data set is forcing U, forcing U, forcing U, forcing U, and the forcing changes, right? I mean, you have the input-output pairs of our data set is epsilon I, well, U0, okay, U0 I. This is the input, and then the output is UI.
Yeah, this is a bit. My point is that this is a bit strange setup for deponent to be forced into. This is not a natural setup for deponent, because deponent is designed where the forcing is a fixed function. So if you take different forcing functions and you take the average performance over different forcing functions after single training, then that is a honest comparison to deponent. If you say I'm going to fix the forcing to a random variable and check at different realizations of the random variable, that's a bit unnatural setting to force the deponent into. It seems like the experiment is pushing the deponent into a very tight corner and then comparing to it.
Deponent is very, I mean, to be honest, it's very disappointing, deponent. We have tried to push it very hard because it was the worst performing model out of all. And we actually tried very hard to make it work. But no matter how hard we tried, it was very complicated to make it work. Actually, we looked at also deterministic PDEs without forcing, because the model can work also for deterministic PDEs. And DeepONet, it was very, I mean, very hard to train and to make it work. Maybe we did something wrong, but it's yeah.
Yeah, I guess my point is that to compare against DeepONet, the experiment needs to set up, I think, a bit differently. To see the power of DeepONet, the experiment has to be somewhat different than what's in this slide.
Okay, so you're saying that for DeepONet, the natural setting would be to
natural setting for DeepONet would be to say that, okay, I have a bunch of I have a space of forcing functions.
Yes.
And I want to look at the average performance over sampling forcing functions.
Okay.
After a single train, you're allowed to train only once, but I will test on multiple forcing functions sampled from a space of functions.
Right.
That is the natural place where DeepONet is powerful. So, but here it seems that is not the case. This slide is giving me the feeling that this is.
I see. So basically what you're saying is that if you're computing if you're measuring performance in terms of mean squared error,
yes,
over where the expectation is taken over the distribution of the random forcing, so you're averaging the action of the, well, not the action, but the effect of the forcing, then DeepONet is supposed to perform well. But if you're actually looking at the pathwise sample by sample performance, then okay, that maybe that's explained.
Yeah, so I have a feeling this, that's what I'm trying to, I think we need to, I'm a bit of a DeepONet fan. I think this is unfair to DeepONet, this slide.
Okay, but if you're average over distribution of forcing, I mean, I mean, DeepONet is compatible with these experiments, but perhaps it's the.
Yeah, I think the experiment has to be redesigned to compare to DeepONet. Is my feeling currently.
Well, but I mean, I would say that the task of learning the pathwise function is much more complicated than learning. I mean, if you do a good job pathwise, it's clear that you're going to do a good job in expectation, right? And the problem is that actually, the other way around is not true. So that's the problem of DeepONet.
The problem is the conventional optimization. That's the whole different thing. You can do pathwise great, but then for every path, your runtime just keeps increasing with the number of paths. If you want to do good on 2 paths pathwise, your runtime is basically double. Your runtime scales with the number of paths on which you want to do well in.
Yes.
And DeepONet does not. DeepONet will not scale with the number of paths you want to do well in. It will on an average do good without scaling the runtime with the number of paths.
Okay.
And that is the trade-off that DeepONet gives. So that
DeepONet,
is why.
DeepONet, the evaluation of DeepONet has the same complexity, no matter if you average over 500 samples or 5,000 samples.
Yeah, so it's like the runtime does not scale with the number of paths. It's on an average over paths, it will do better for a single run.
Okay.
So DeepONet's trade-off is a bit different from NSPDs, I think.
Okay.
So I think this experiment is a bit slightly unfair to DeepONets. This experimental setups are slightly unfair to DeepONets, I think.
Yeah, maybe. Bunch of questions on the chat.
There are some comments on the chat, yeah.
Maybe you can unmute yourself and ask, because I don't know where to look.
There are many comments by Juan Sotelo and Itamar. Did you want to unmute yourself?
Good morning.
Hello.
Yes,
Yes.
Yeah, we hear you. Yeah.
Yes, the question was about, well, you were talking about the influence of noise in the dynamics you were analyzing. And so my question was, what happens if the noise is coupled to the dynamics of the system you're analyzing? And how would that change? And more or less, I think I got a partial answer from Professor Halevi, where he mentioned that, well, solving such a situation might be complicated or even ill-poised. So probably one needs more information about the system and the noise in that particular case.
so you think the noise, when the dynamics influence the noise, it's not that the noise
Yes.
influences the dynamics.
Yes.
So is there any, you have in mind some special example where the what does it mean the dynamics influence the noise?
Well, I was thinking more in terms of a kind of biological systems where, I mean, usually those systems operate under a lot of noise, but there is also kind of, I mean, in this kind of evolutive processes, you might have this coupling between the noise and the actual dynamics that is occurring there. I mean, that's the example more or less that I have in mind.
Yeah, so maybe, I mean, basically then you have a coupled, you have somehow U that is a function of the noise, and you have the noise that is a G of U, something like that.
Exactly, yes.
Okay, perhaps what you can do is that you can consider the augmented state, U psi, but then depending on what kind of dynamics you have, yeah, I will have to think about it, but yeah, I don't know on top of my head, but if you can maybe, because you know, if you consider something like in the case of ODEs, I don't know where to write, like here, what is, you have dx equals f of x y dt, and then you have dy equals g of well, x y dt, right? And then, well, you can consider z equals xy and write dz equals, well, something like fg. Well, that's a matrix, but maybe it's like 0 g something, g 0 0 z dt, right? Or something like this. You augment the dynamics and you have a system for the augmented variable. I don't know if this can be done for SPDs, but yeah.
Okay, thanks very much.
In any case, you will need to reformulate the framework totally.
Yeah.
Because this biological system that you're talking about are, of course, very interesting. However, they're more complicated than the straightforward theoretical framework that we have here, that going step by step. One more comment, I'm not a professor.
Oh, I'm sorry. Okay,
So
okay.
Thank you for the promotion. But I don't need
Right.
it. I'm just enjoying these discussions and learning.
Okay, me too, thanks.
In both senses, learning.
All right, okay.
And actually, I wrote you email some time ago and I got no answer.
Well,
but that's between the two of us.
Right.
Maybe further later.
Okay,
other
thanks.
questions or comments?
Yes.
Yeah, okay.
I was fortunate to have lectures by, I believe his name was Robert Taylor from University of Alberta. And that was kind of 15 or more years ago. He wrote also a book, and he talked a lot about Zakai equation, but he has totally different mathematical approach. And I believe it will be interesting to do some kind of comparison or to see how the two are related. So he has a book and maybe about random processes or whatever. And Ito Stratanovich, I think during your talk, there was going from Stratanovich sense to Ito, and then somehow back. And the difference between the two approaches is very, very interesting and quite difficult to follow what exactly the difference between the two approaches or formulations. And somehow, if I will insist on one of them, for example, if I just vote for Ito, how can I deal with your talk and vice versa?
So rough paths. The rough path above Brownian motion, it's the Stratonovich rough path. So mathematically, what you get is that the geometric, technically, the geometric rough path, that is the limit of this sequence of approximation, is Stratonovich. It's not Ito. Now, but the thing is that from classical stochastic analysis, we know that any Ito, any Stratonovich SDE can be turned into an Ito SDE, provided that you add to the drift a correction, okay, that is explicitly computable from the vector fields, from the drift and the diffusion. So you get, but the problem is that the Ito solution of the SDE is not in any sense a geometric rough path. Is a rough path, which is there is geometric, quickly geometric, there are a family of different rough paths, but it's not a geometric rough path, which is like the nice rough paths that people use in order to solve differential equations. So the way they do it is that you get Stratonovich in the rough path sense, and then you have this correction to go back to Ito. But then Ito is not really a geometric, is not a geometric rough path. It's a rough path, but belonging to a larger class of rough paths. So that's basically the way I reconcile the two views.
It's very beautiful answer, but I will be happy to see it in writing, because this kind of differences are blurring the pictures for most people.
Okay.
And I volunteer to be a leader of the confused.
Okay. Yeah, I think it's I'm happy to get a board and write it down if there is an occasion to do it. Yes.
Appreciate it. Thank you very much.
No problem.
In the
Yeah,
there was the Duganov version of the stochastic ODE paper, right? And in there they had to use this Euler-Murayama instead of, Euler Stratonovich instead of Euler-Murayama because it somehow facilitated the backwards pass. Is that relevant in this SPD setting?
Sorry, say it again. Sorry, you mentioned in one of the Neural SDE or ODE paper, they use a numerical solver instead of another one.
Well, for the, I don't remember the details of this, but I think in the forward pass they couldn't use Euler-Murayama because it wasn't symmetric in time.
Yeah, I think in the first Neural SDE paper that Duvenot and all these people from the Neural ODE community did, I think they got into a big mess with Ito, and they, to do the backpropagation, they had control. I mean, I'm being honest. I think that paper is a bit complicated. For me, it's very complicated to understand. But with rough paths, things just becomes so much easier, and there is no much issue in getting the adjoint process and obtaining the backpropagation. So I'm not I don't think I can comment too much on I think you're talking about this latent SDEs paper. No, I don't remember exactly the title, but we can find it. But yeah, I don't know if I can add much more to this, but
Thank you.
All right. Other questions, comments? Okay, then let's thank the speaker and thanks everyone for coming. Thank you, Chris, for the nice talk. Yeah, thank you. Bye, everyone.
Thank you. Bye-bye.